Hi everyone, I hope you are doing well. In this video, I will explain how computers read text. So, to understand this, we need to understand how text is represented for computers. In the first place, we'll talk about one-hot vectors, count-based vectors, n-grams, TF-iDF vectors. After that, we'll talk about embeddings like word2vec, glow, FastText, ELMo embeddings, and attention-based embeddings. Let's start with the one-hot vectors. So in these vectors, we have only ones and zeros. Ones if words exist and zero otherwise. So if we take this example, in our vocabulary, we have three words, which are red, green, and blue. And we have here three documents. Each document contains only one word. For example, for the document 1, we have only the word red. Document 2, we have only green. And in the third document, we have only blue. So we put 1 in front of the word contained in the document and zeros in front of the other words. And the same for document 2 and document 3. So it's as simple as this. So at the end, we will have a matrix with only zeros and ones. Now, the problem with this technique is that we don't have words count. It means if the first document, for example, had the same word read many times, we wouldn't have the number of times that the word read exists in the first document, but we have only one and zeros otherwise, or other numbers in front of other words. Another problem is that at the end we will have a sparse matrix. Here we have a small example with 3 documents and 3 words, but if we had far more words, we would have had a far bigger matrix with only ones and zeros. Another problem is that we don't keep the context. It means here our vocabulary is represented as a bag of words. It means we don't have the neighboring of these words. And also we don't have semantics. It means we have the word red, green, blue represented by a vector with ones and zeros, and you don't have any idea about the meaning of these words. In the second place, we'll talk about the count-based vectors. In these vectors, we have words frequency. So if we compare them with the one-hot vectors, at least here we have how many times a word appeared in a document. So if we take this document, we have the word about appeared only once, bird 5 times, and so on for the other documents. But we still have drawbacks like the sparsity of the matrix, as we have count here, but we still have zeros when the word doesn't exist. We don't have context either because we still have bag of words, and we don't have semantics either. Now let's talk about n-grams based vectors. And before going into details, let's explain what an n-gram is. So an n-gram, you can see it as a group of words actually. So if we fix n to 1, if we take this sentence, this is a sentence. So the different unigrams are the words taken separately actually. So it's gonna be this is a sentence. Now if we fix n to 2, we'll have bigrams, and bigrams are like this is a sentence. It means we take the words following words 2 by 2. That's gonna be the same thing for trigrams. Now, what makes these vectors different from the other vectors? Once we have vectors of n-grams in this case, we have the frequencies though, as what we saw in the count vectors, and we have more context because we take the neighboring words with the actual words, but we still have some drawbacks like the sparsity of the matrix, and we don't have semantics either because we don't have any relation between words, or we don't know the meaning of the word, but we only have vectors of frequencies. And at the end, we'll have a matrix like the one that we saw in the previous slide, but we just have the n-grams instead of the words. Now, let's talk about the TF-iDF vectors. These vectors are built using the TF-iDF scores, which are computed using this formula, which is the TF for term T multiplied by the log of N divided by the DF for term T. So all this term is actually the IDF. So now let's see what each term stands for. For the TF for the term T is the term frequency of the term T. It means how many times that the term occur in the document. For the N is the number of documents in the corpus, knowing that the corpus is actually a collection of documents. For the DFT, it's the document frequency of the term T. It means how many documents have the term T actually. So now let's see how we multiply these terms. For the TF, it's actually a matrix of words that we've seen in the other slides, but we count the term frequency. Just here, assume that we did some calculations to have smaller numbers. We multiply this TF matrix by the IDF vector, and at the end we'll have a matrix like this one, which is the TF-iDF matrix. Now the question that we ask here is that what makes this technique better than the one that we've seen so far? This technique actually affects scores to words to rank their importance within a document. It means words with higher TF-iDF scores are more important words within a document, and this helps us in tasks like document classification tasks, in natural language processing, for example, which is a subfield of machine learning. In the document classification task, actually, we are asked to classify documents under some classes. And when we have words which distinguish some documents from other ones, it becomes easier to classify these documents under a certain class. So this technique helps very well in such tasks. So this technique helps to point out some more important words, and at the same time it gives lower scores to words which don't distinguish documents. But this technique still have some drawbacks that we've seen so far, which are the sparsity of metrics, because we still have the same problem. We don't have a context here either, and we don't have semantics. Now let's talk about word embeddings. These embeddings are actually dense vectors, which are vectors with small and fixed dimensions, the opposite of sparse vectors. They are dense because, as you see with these words, we have vectors of 7 dimensions in this example, and each dimension represents actually a feature. Like here we have living being, human, gender, royalty, verb, and plural, and each feature describes the word in some way. For example, as you see here, we have positive and negative scores. Here, for example, we have 0.6 for living being, and we have -0.3 for the feature verb. It means that a cat is closer to living being than to verb, and the same for the other words. And having a smaller dimension is a big advantage compared to the other sparse vectors. Here we have a toy example, but generally we have dimensions which vary from 50 to 300 and even more. Now, another advantage of these vectors is these vectors keep context. Actually, it means they keep the neighboring words when we teach the model in the training phase. Another advantage is with these vectors, similar words have similar embeddings, and if we take the same example and we represent these 4 vectors in a 2-dimensional space, we see that cat and kitten are closer to each other compared to dog, because these words have more similar embeddings compared to the one that the dog has. And with these embeddings, distance between words becomes more accurate, as we've seen in this example. Another advantage is that with embeddings like word2vec and glob that we'll see in the next slides, we have analogy between words. It means if we take these 4 words and we represent them in a 2-dimensional space as well, if we ask the model to predict this word, which is the word king, by giving it the word queen and giving it the information that the relationship between these words to be predicted and the word queen is the same as the relationship between men and women, and giving this information to the model, it will be able to predict the word king. And this is how we have analogy between words, and this is because the model learned analogy between words during the training phase. And thanks to all these advantages, word embeddings were a revolution in the NLP field, which happened in 2013 with word2vec vectors. Now let's talk about word2vec embeddings. These embeddings are word-level embeddings, like what we've seen in the previous slides, and we have 2 variants of word2vec. The first one is SIBO, where the model, word2vec is a model actually, where the model learns to predict a word giving its neighboring words. In this case, the word has 2 neighbors on the right and 2 on the left, which we call the context. On the other hand, the skipgram model predicts the neighboring words given an actual word. And one major aspect in the word2vec model training is that the model has been trained using positive and negative sample for positive and negative examples. For the positive samples, we give the model a word and its neighboring words, and we ask it to predict that these words are the neighbors of a given word. And with the negative samples, it's actually the opposite thing. Now, these embeddings have their drawbacks as well, as we have what we call the OOV, or the out of vocabulary words, which are words that the model didn't see during the training, and they don't have individual embeddings like what we have with the words that the model see in the training. Another drawback is that we have, with word2vec, we have a fixed context window. Like in this case, we have context window equals to 2. It means we have 2 neighbors on the right and 2 neighbors on the left. Another drawback is that we still don't have word-based semantics. It means that a word has only one embedding no matter the context. After the word2vec embeddings, GLOVE embeddings appeared, and GLOVE stands for Global Vectors for Word Representation. These embeddings are word level as well, and compared to the word2vec embeddings, these embeddings are based on words concurrence. If I give you an example, if we take these 3 sentences, I like deep learning, I like NLP, and I enjoy flying. So here we see that the word I appear 2 times next to the word like. So that's why we have 2 here between I and like, and we have 1 between I and enjoy, because we only have 1 time I enjoy, and so on for the other ones. Once this matrix is built, we apply matrix factorization, and we'll have an embedding like this one for each word. One of the advantages of these embeddings is that they consider the whole corpus compared to the word2vec where the context is fixed, but these embeddings have their drawbacks as well, which are the OOV problem that we've seen with word2vec and no word-based semantics either. Now, GLOVE embeddings were followed by FastText embeddings. These embeddings extend word2vec, but the main difference between FastText and word2vec is that FastText is based on words and subwords. So if I take an example of the word eating, during the training we give the model the word eating and we give it its subwords, which are EA, EAT, ATI, TIN, and so on. And if you notice here, for the first word and the last word, we give these 2 samples to indicate the beginning and the end of the word. And to give you a deeper comparison here with skipgram word2vec, as we've seen in word2vec training, we give to the model the context of a word if we consider that here we have a context equals to 1, so we have the left word and the right word, and we ask the model to predict the word like. And here, to compare more in depth word2vec, skipgram, and FastText, if we consider this sentence, which is I like natural language processing, in word2vec we give the model the neighboring words, like in this case I and natural, for the target word like, and we ask the model to predict the word like. But with the FastText model, we give the model all the subwords neighboring word, and we ask it to predict the word. And another detail here is that we give the subwords and we give the word itself. With this technique, we have larger and open vocabulary. It handles out of vocabulary words, because even if the model don't see the word during the training phase, it can split the word into subwords, and for sure these subwords were seen during the training phase. Another advantage is that with this technique we capture morphology for the same reason, because we split the word into subwords. Another major advantage here is that we have variable context window, as we don't know how many subwords we'll have in the neighboring, like in these examples. Now, this technique isn't without drawbacks, because we still don't have word-based semantics. Now, let's talk about ELMo embeddings. ELMo were another revolution actually in the NLP field, because these vectors are contextualized, and also we have word-based semantics. It means a word has more than one embedding depending on the context. So we solve one of the problems that we've seen in the previous slides. A part of these advantages, we have bidirectionality as well. Now let's see how we have all these advantages using this example. So here we have the sentence let's stick to, and we build the embedding of the word stick. For this we have bidirectionality because we look at the left context of word stick. So if we have the word stick here, we have its left context from here, we have its right context from here, and after that you concatenate both contexts. And here we have two layers in the network, two hidden layers. I won't go into details about hidden layers and layers of neural networks, but don't hesitate to ask for it if you need it in the comments. So we concatenate as well these embeddings of the other hidden layer, and we concatenate as well here the embedding of the word stick. Once it's done, we multiply each vector by a weight based on the task in the second step, and in the third step we sum up all these vectors. And with this we have bidirectionality, we have context, and we have word-based semantics. The last embeddings that we will see in this video, but not the least, are attention-based embeddings. These embeddings are contextualized. We have word-based semantics as well, but the major advantage of these embeddings is that the model focuses on the relevant parts of the input sequence. Let me give you an example from the translation task. So here we have a sentence in French that we want to translate in English. If you notice here that we have dark and light squares, so words with lighter squares are more relevant to each other compared to the other ones. It means if we take the word accord in French, its translation in English is agreement, and it's the same thing as in économique européenne. We have European economic, and one of the awesome things that we have with these models is that the model was capable to see that économique européenne becomes European economic. It means it put more attention on the word economic translated to economic, and it put more attention on the word European to translate it in European, even if to translate a sentence from French to English, we don't necessarily keep the order. So this is very important to note. This is one of the most important aspects of the attention-based embeddings. We also have bidirectionality in models like BERT or the other BERT-based models. Don't hesitate, guys, to ask me in the comments to make a video to explain the BERT-like models if you need it. And this attention concept, guys, is the core concept of the best and newest models that we have in NLP field. So thank you guys for watching, and don't hesitate to leave a thumb up if you like the video to have more videos like this. I will put all the links that I used to prepare these slides in the video description, and don't hesitate, guys, to leave comments if you need further explanation about concepts that I explained in this video. Thank you guys, and see you next time.